on this computer. All right, hi everybody, hi everyone on record. Yingi, can you enable screen sharing for me?
Sorry? So you cannot really do it as a co-host here?
No, it says host disabled participant screen sharing.
Okay, and then I will set you as the host so you can do everything. Okay, now you can do it.
No host now, nice. Cheers, Ying.
Cheers.
Okay. So, we are working on the Back to Basics notebook in Colab, following on from the last couple of weeks. I think this is our 4th week of this particular sort of series of tutorials. If anyone needs the link to the Colab notebook, then you can find it on the Slack channel if you're part of the MIB Slack channel, or you can find it on our GitHub page underneath tutorials and the Back to Basics Python notebook. And fingers crossed it will load in my browser this time. But anyway, there's a link in there to the Colab notebook. Here we go. So if you need to quickly find it, then there's a link there, and there's a link in the Python channel here. Okay, so hopefully everyone can have a link to that, and if not, send a message and I'll just send it over the chat. So in our last couple of tutorials, we looked through, I made a couple of notes, we looked through string processing, dictionaries, nested dictionaries, all with the application of looking at a particular protein, both its sequence and its 3D structures and so on. We looked at a couple of bash commands, which is a command line shell scripting language, which is particularly useful for doing little bits, like for example, downloading a file. We use that to download a .pdb file, which contains the 3D coordinates of atoms within a protein. We did some filtering to filter out just the coordinates from that file. And we started looking at distance measures between two atoms there, and that's where we'll pick up from today. So somewhere down the notebook there is a header that says part 4 or something along those lines. Okay, so here we go. Okay, so I haven't explicitly labeled it part 4, but I think we roughly finished off on distance in 3D space. And I think the last exercise we did was to measure the Euclidean distance between two atoms. And Euclidean distance just means direct distance, as the crow flies. It can be applied to 2D space or 3D space. It looks exactly like the Pythagoras distance between 2 points in a 2D plane, just with an extra dimension wedged in there. So the exercise that I gave you was to write a function that can calculate the Euclidean distance between two atoms. And what I didn't do was tell you how to do a square root, which was a huge oversight, and I'm quite sorry for that. So briefly, the easiest ways are to import a square root module either built into Python. So for example, from math, built-in Python module, import square root sqrt. Alternatively, NumPy, our numerical Python module, also contains a square root function. So those are the two ways of doing exactly that. You'll see that in this little section here, I've done np.square root. So I'll be using the NumPy implementation of that. Okay, so that's where we got to. We made a simple function that finds the distance between two atoms. This error that I've just got from running this cell is a result of me not running all of the previous cells. So this variable that I'm referring to, coords, doesn't exist yet. So let me try and find the run all button. Okay, I'll just give that a second. Okay, so we looked at doing one distance measure, and over the next couple of tutorials, I want to look at the distances between all of the atoms in our protein structure, so that we can then find out which atoms are close enough together so that it's probably a covalent bond between them or a non-covalent bond. So we'll be calculating distance with a view for doing bond analysis and then finding patterns within the structure that way. The issue with doing lots of distance measurements is that for every atom that you add to your set of atoms that you're measuring distances between, the number of operations that you have to do squares. So if I've got 4 atoms, then the number of measurements I have to do is 4 squared, and so on. Although it is worth noting that about half of those are repeats. So there are ways that we can trim down our calculations to make it simpler. But in the meantime, I'll quickly introduce you to a quick pairwise function. So in this cell, heme chords, in this cell, we create a object called heme chords. It's located from a data frame that we defined previously. From memory, I think the data frame was, I think it contained the coordinates of all, the whole atom section of the PDB file. So we can see we're locating the data frame by whether or not the residue name is hem, which is the heme cofactor in our structure, and then we're also locating it by columns X, Y, and Z for X, Y, Z coordinates. You'll notice that I've also stuck dot values on the end. So sticking dot values on the end of a pandas object returns you the underlying NumPy object that sort of drives pandas. You'll notice that it doesn't have parentheses at the end like it would if it were a function. It's just an attribute. So by calling values, we get this, as opposed to this. So we're still dealing with 3D coordinates, and the shape of our object is 86 rows by 3 columns, X, Y, Z, and 86 atoms. So this brings us to our first exercise of the section. Your task is to write a function that for each coordinate in heme coords, an 86 times 3 NumPy array, find the distance to every other atom. I've dropped a hint in there. You'll have to use, well, I suppose you don't have to use, but you could use a for loop within a for loop. So for example, loop over each atom, for each atom, measure the distance between that and every other atom. But if you can think of a more efficient way to do it, then definitely do. And then test the function on the heme coords object to find the distances between each atom in this, in the heme. Okay, I will set a timer for 5 minutes. 5 minutes. All right, off you go. Any problems, then give us a shout or message in the chat or something like that. And I'll see you again in 5 minutes.
Abby is I have a question about this. What is the output of this? Is it a list? So for every entry in the array, you're gonna get a list of all the distances to the other atoms. So is it a data frame that we're getting out, or?
It can be either a list of lists, a data frame, or a NumPy array.
Okay.
But yeah, good question.
Okay.
Cheers, Dave.
Do you know you're muted?
Yeah, I know. but yeah, I might forget. Yeah. How's everyone getting along? I didn't even remember to do the countdown timer. Okay, time's up. Okay, I'll start going through the answer. Well, a potential answer. So I've started writing out the function already. So I've defined it as pairwise distance. And at the bottom of the cell, I have a line that runs it on this array chords, which I've just remembered is not the aim of the exercise. Instead, I'll run it on heme chords, and that's good because running it on the larger array chords could potentially take much longer because of the complexity increases that I mentioned earlier. For atom in array, okay, so this function takes in the array, in this case heme chords, which will look something like this. And then we start looping through each atom in that array. So the naming systems that I'm having here, that I've got here, are going to be for the outer loop. I'll name everything 1, so atom 1, distance is 1, and then for the inner loop, I'll name everything atoms 2. How about that? Okay, so outside of the first loop, I'll make a empty list called distances1, which I will then populate with lists of pairwise distances for each atom. So we're going to get a list of lists out of this. which then we can turn into something like a NumPy array if we want. So for atom in array, distance is 2. Let's call that atom 1. I hope that makes sense. I probably could have thought of a better way to name inner and outer variables, but let's roll with this for now. Okay, so for each loop, we then create another empty list, just like we did before, and then loop through the array once again. So we have this variable atom1, and you know what? Just to get a look at what's going on, let's print that as we run it. See what that does. So it print each time atom1 is the 3D coordinates of that particular atom. Okay, cool. Then we'll loop in again for atom2 in array. So now we actually want to calculate some distances between atom1 and atom2. So distance equals, and at this point I'm going to steal a function that we made in the last tutorial, distance between atoms A and B, in which case A is atom A and B is atom B. Other option is to use the built-in numpy.linalg.norm, which is exactly equivalent and easier to use, but I'm going to go for the one that we wrote. Okay, atom1 minus atom2. No, sorry, they're supposed to be separate variables. So yeah, we're calling back to our function. It takes in atom1, comma, atom2, and returns the distance between them. Okay, so that's what we're doing. So at this point, we need to append our distance measure to distances2. So distances, let's try that again, distances 2 dot append our distance measure. And then following that, so after the inner loop, now we have a list of distances named distances2, which we will then append to distances1. Distances1 dot append. Okay. So by the time both of these loops are run, we should have distances1 as a list of lists, which we just now only need to return from the function. So return distances1. Let's go. Okay, what have we got here? So we can see by the end of the output that there's 2 ending square brackets, which does indicate that it is indeed a list of lists. And we can see here where one list starts and another ends. Okay, that's good. It would be easier to work with if we package this list of lists into a NumPy array. So np.array, we will call around this list of lists, similar to how you might construct a data frame around a list or a list of lists. And if you would prefer to work in a data frame rather than a NumPy array, then feel free. Now we have this distance matrix. Let's save that as a variable. Let's call them team distances. Yeah, with good spelling this time. So if we've done it right, it should be a square array that is the same number of rows as columns. So the acid test is to call the dot shape on it, and we get 86.6. For extra interest, if we want to get a feel for what these distances are actually like, we could probably plot a histogram of these distances. So just as a quick aside, I'm going to import matplotlib because .pyplot because I am not sure if I have already. And then I'm going to make a simple histogram on heme distances. Except before I can do that, well, actually, I'll start constructing it and see how we go. Okay, so I'm expecting an error here. Okay, so not so much an error, but more an unexpected result and lots of colors. So PyPlot will treat different dimensional arrays, in this case a two-dimensional array, differently to say a one-dimensional array. So we're going to call .flatten on this heme distances so that they all get equal treatment. And there we go. You can see there are two groups of different distances between these atoms in the heme coordinates. If we want to increase the number of bins or increase our resolution, if you like, we can call bins equals, let's say 30. Remember, we only have, well, we have 86 atoms, so that squared, let's go for 15. Let's see what that's like. And there we go. There's the distribution of distances between atoms in the heme cofactor. Cool. Okay, moving on. So we now are starting to get to the problem of computational complexity, which is a pretty large subject area. So I'm only going to cover it. I'm going to touch on it. So in this cell down here, I have imported from my answers file two different possible pairwise Euclidean distance functions from a file that you can, from Back to Basics, which you can find in our Python Club GitHub. I import time, I import matplotlib for plotting, and also tqdm, which provides a progress bar. I use a useful trick in NumPy, mp.linspace, which evenly spaces numbers between a start and a stop, and then you specify how many intervals you want. So in this case, I have an even spread of numbers between 0 and 3000, and I've got 5 numbers between that. And then I build a loop. So to use a progress bar in a loop, you wrap the iterable that you're looping over with tqdm, and then that will print out a progress bar like this. So within the loop, a timer is started, and a variable t1 is set, and then distances are calculated between the atoms that we've sampled. So our sample size will start off as, say our sample size is 100, then we'll sample 100 atoms from df using df.sample. And to ensure that, so sample only takes integers, so I round our number probably up with int, but other functions are available, particularly the round function. And then I locate the XYZ coordinates. And then for all of that, I calculate the pairwise distance. And then I stop the timer. Then I add it to this list up here, results, and then plot that. So the idea of this experiment is to illustrate how the amount of time that it takes for the computer to do the job increases non-linearly with this job in particular, but there are quite a lot of other jobs that also scale non-linearly, and it's worth being aware of that sort of problem, which often isn't an issue for small sample sizes, but then once you start to scale it up to something quite large, like in our case, the whole of a protein of about 8,000 atoms or so, then you get some fairly significant slowdowns. And that's what you see here. You might remember that the first couple of iterations were fairly quick, and it roughly increases with the square of the number of atoms that we're calculating. So that's something to be aware of, but luckily there are solutions to that. One of the solutions that we'll be looking at today is in the library Sci-Fi, which we will be visiting again in the future. Sci-Fi is one of the core Python libraries, which has many functions, including functions for signal processing. So for example, it can be used for smoothing UV vis absorbance traces like we would have gotten last time, or for example, I've seen it be used for mass spec analysis and stuff like that. It can be used for optimization or curve fitting. Say you have a function that predicts something useful and you want to find the optimal inputs to that function to get the maximum output. And that's an example of when you might use that. We have integration functions, linear algebra, and the focus of today will be the spatial algorithms for 3D geometry, essentially. Although it's worth noting that whilst I say 3D geometry today, it can be extrapolated to 2D, or it can be extrapolated up to 4D, 5D, and so on. If you want to take a look at our previous encounter with Sci-Fi, then check out this curve fitting tutorial. Today we'll focus on the KD tree algorithm. I've dumped the Wikipedia link to a KD tree in there, so if you're more interested, then follow up that link. But before we get to any actual computing, it's worth talking about installation, especially if we're going through basics. So my hope with this section is to not only teach you how to install Sci-Fi if you don't already have it, but also install just about anything. So installation generally happens via the Python package managers, and by package managers, think the App Store. Python has built-in package managers like the App Store, namely pip, which is the de facto package manager for Python, and Conda, which some of you may be familiar with if you've installed an Anaconda distribution of Python. So pip is the standard Python package manager, and not only can it be used for installation of files locally, but it also gives you access to the PyPy repository, which, here we go, let's go to their website, which contains many free Python packages. Like for example, if we didn't already have pandas, then we can find pandas in here. Or if we want to find something like PyTorch, a machine learning library, then we can just as easily do that, and so on. So that's one place where you can find fairly task-specific Python libraries. And one thing that you'll notice on the PyPy website is this copy and pastable command at the top up here, pip install PyTorch. That's the general syntax for the command line commands to install packages. So I won't use it on PyTorch in this case, but in the case of Sci-Fi, it will simply be pip install Sci-Fi. But normally the PyPy website is a good first port of call for finding out exactly where to install this from. Okay. Similarly, if you want to uninstall a package, then you can use pip uninstall. And if you want to search for a particular package, then you can do exactly that. So you might remember if you were in one of the previous Back to Basics. Yeah, Ying Ying.
Hi, James. I have a question, maybe two.
Yeah.
The first one is like, for this pipe install some software, and this like a command line is used in the terminator, or it's in the Python itself?
Yeah, good question. It's a terminal command.
Oh yeah, terminal, it's not terminator.
So, but you can run it through Python if you want, which will be part of the exercise. So I'll switch over to my terminal and I'll demonstrate. Yeah, Ying Ying.
Yeah, okay, thanks a lot.
Okay, yeah. Sure.
I have another question, if I can ask.
Yeah.
Yeah, it's previously a friend introduced a thing called EVN, Environment Python or something.
Oh yeah.
Yeah,
Would you like to
I currently I know how to do it, but I just want to mention it is to confirm if not confirm, it's just to see if it's a good way to run the Python on a computer, especially when there are lots of different projects. Yeah.
Yes, is the short answer. There are a couple of ways of running environments. I'll touch on that after we do a couple of commands, and if I forget, remind me. But
Okay,
yeah,
thank you so much.
That's a good point. That's all right. Okay, so we're in my terminal, which is another name for a command line. If you're on a Windows computer, then by searching in the search bar CMD, it should come up with something similar. The commands here with pip are not operating system dependent, so it's the same for Windows, Linux, Mac, etc. To search for a module, then you simply type pip search Sci-Fi, say, and it will give a second. It will query the PyPy database for the search terms and then return me a list of modules that I can then install. So you can see here, Sci-Fi for me is already installed, and then if I want to install, say, number Sci-Fi, pip install number Sci-Fi, and so on. So that's the gist of the command line arguments. Okay, and very briefly, I'll talk about Conda before we move on to our second exercise. So Conda, similar to pip, is another package manager. It has some strengths over pip, namely that you can install non-Python files, whereas with pip, you can only install Python-based projects. So for example, a cheminformatics software RD kit that we use fairly commonly is written in, I think, C++, or at least large parts of it are. So Conda will allow you to work with something like that, as opposed to pip, which will only let you work with purely Python-based projects, I think. So Conda is the package manager included in Anaconda. So like I said, it can install binary files. The other advantage is that it has a slightly more sophisticated compatibility checking between packages. So for example, say I install Scipy with Anaconda, it will check for incompatibilities between this version of Scipy and all of my other packages, whereas pip will not go into such detail as Anaconda. Yingying mentioned environments earlier, and an environment is a useful tool for experimenting with installs, or having an area where you can install experimental packages without worrying about it clashing or doing anything strange to your regular working environments. So perhaps we'll go into that in a full tutorial at some point, but in the meantime, I've left a small cheat sheet left by the Anaconda documentation, which is a pretty good reference. Okay, exercise 4.2, let's go. So we'll be using pip again. In the cell below, using what you know about bash commands, and if you weren't in previous tutorials, then have a quick scroll up. Actually, I'll talk through what during the exercise as well. Your tasks are search PyPy for SciPy, search it for scikit bio, and whilst you're at it, try searching for other keywords, because not only does it help you search for package names, but also keywords, like for example, bioinformatics or something. And finally, use pip to install scikit bio to this Colab runtime. If you're running this notebook on your local computer, then don't feel like you need to. That's fine if you don't want to mess up your current working environment. That's your exercise. I will give you 2 minutes, 3 minutes. I'll do 2 minutes because we're coming up to 1 o'clock. Okay, off you go. So if you weren't in the, I think it was part 2, where we covered how to run command line commands in the notebook. Let me quickly scroll up to that. Okay. Okay, so on this section about bash, I briefly mentioned how to invoke a bash command. I say bash command. What I should have said is a command line command, because then that makes it applicable to Windows as well. Question? Sudo. Sudo is what you prepend a command with if you want to do it with admin privileges, but for pip you shouldn't need to do sudo. So the simplest way to do this exercise is prepend all of these command line arguments with an exclamation mark, and then it will automatically make that line of code a bash command. Alternatively, type %- bash at the top of a code cell, and it will make the whole cell a bash cell. I keep saying bash, I mean command line, because bash is not ubiquitous. I don't think Windows works on bash. Okay, 30 seconds left. How's everyone getting along? Thumbs up?
Yeah.
Okay. Cool. I'll start going through it. So, like I mentioned earlier, by prepending your command with an exclamation mark, then it suddenly makes it a command line command, which in this case, because Google Colab runs on a Linux server somewhere, we do Linux or bash commands. So for example, ls will list the contents of the file that we're working in. So command line commands, pip, search, Scipy. That was the answer to question number 1. And you can see that it gives you a list of search matches, and at the very top we have Scipy. It's already installed, so no need to install it. But if we did want to do that, then the command would look like this. And you can see when we try and do that, it says requirement already satisfied. So it already detects that it's already installed and then gives up. Okay, part 2, search for scikit bio. Search scikit bio, easy peasy. You can see quite a lot of results are returned, and if you're interested in browsing packages that might suit whatever your particular needs are, then the pip search is potentially quite a good option for you. Alternatively, finding the sites on PyPy or on Google is also equally viable. And to install a package, in this case scikit bio, pip install scikit bio. The output below the cell is the output that would normally appear in a command line like this, but because of the nature of Python notebooks, it's all just printed out underneath, which is, it's not that visually appealing, but if you really don't like it, then you can minimize the output of the cell with one of the X's. Okay, so that was that exercise, and that brings us on to the final section that I think I'll cover today. I'll talk briefly about Scipy, which should already be installed anyway, and in particular the spatial algorithm that we'll be focusing on, the KD tree. So we saw that the problem with calculating pairwise distances between a large number of points suddenly becomes quite complex quite quickly as we increase the number of points. But there are workarounds and sort of shortcuts, cheats if you like, that are wrapped in some of these clever algorithms. So for this particular problem, measuring distances between atoms, the reason why we're doing it is to find distances between atoms within a certain cutoff. So I guess you could formulate the problem as we're looking for each atom's nearest neighbors, with the assumption that its nearest neighbors are the atoms that it's bound to, either covalently or non-covalently. So in this case, we can use a nearest neighbor search algorithm, the KD tree, which is a shortcut to finding the nearest neighbors of each point in space, and it eliminates the number of calculations that you need to make. How does it do that? Well, before making any calculations of distances between 2 points, initially the algorithm will divide, in our case, this 3D space into half, say with this red cut, a plane straight down the middle, and then those halves get halved again and again and again recursively, until I assume the K is the number of partitions that you make, but see what Wikipedia says. Okay, and then after you have partition space into these small chunks, then you can calculate distances between atoms only within these small partitions of space, which means that you're only calculating distances between atoms that are actually nearby to each other, and it saves you from calculating the distance between an atom at the complete opposite side of the 3D space that we're working in. For more information on the algorithm, check the KD tree Wikipedia page, and also give YouTube a search. There's plenty of good videos that explain it nice and succinctly. So we'll take a little look at the Sci-Fi implementation of the KD tree. So this link here is a link to the documentation for this particular function. So it's under scipy.spatial.kd tree with caps. You can see on the documentation page, it says the input that the function would like. Sorry, I say function, I mean object. This is an object. So it takes in the data array-like. Oh, that's perfect. That's exactly what we've got. So we'll feed it the coordinates to our protein, which we called coords. So we'll remember that, yeah, we have this array coords. And then we want to make one of these trees. So I've realized that I've actually missed out the code that I had in my local version of the notebook. So if you're interested in seeing what should be there, check the GitHub. So this is what I should have put in: from Sci-Fi Spatial import KD tree. So what does that do? Import. So what we could do is import Sci-Fi and then go scipy.spatial.kd tree to access this object. Alternatively, we could from Sci-Fi Spatial import KD tree. Both are perfectly viable. For the sake of consistency, I'm going to go with what I did in the original file. And then you can see underneath here, I initialized the object KD tree with the alias KD on the coordinates, the protein coordinates. It doesn't take very long to run. The object is initialized around coords. Now the question is, oh, okay, great, we've got this object, a KD tree, which is our sort of data structure, which groups points together based on where roughly they are in space. How do we use it? So when I get stuck, I often ask for help directly to the interpreter. So the help command called on either a package, a function, a module, an object, will return a doc string of that object. So in this case, if we were to run help on this object that we've already initialized, then we'll get the doc string for our KD tree. So your exercise in this section is to find help with the KD tree object, And then scroll through the help documentation to find out how to find the sparse distance matrix between points. By sparse distance matrix, I mean a matrix that is mostly zeros, and because it's mostly zeros, you might as well not bother explicitly storing all of the zeros. So instead, you just store the coordinates of numbers that aren't zero, and of course the number itself. Why do we have so many zeros in our case? It's because we're only calculating distances between atoms that are actually close to each other, and then we don't bother with the rest. That's why it's mostly zeros. So the zeros aren't a result of the distance being zero, it's just a result of an unknown. So yeah, your exercise. Find help on the KD tree function. Find out how to get the sparse distance matrix between points with coords, and then find the sparse distance matrix. Not included in your notebooks is this currently, this command, so you'll also have to enter that yourself before any doc strings can load. Okay, I will give 3 minutes. We'll give it a go with 3 minutes and see how it goes. 5 minutes, sure. Okay, you get 5 minutes. Cool. Any questions? Then shout them out, drop them in the chat, something like that. I'll be keen to answer some. Good luck, and off you go. Okay, how's everyone getting along? Almost out of time. Alex raises a good question, or sorry, a good point in the chat. We'll come on to that after we have run through the answer to the exercise. Cool, okay. So, you just move the chat to one side. What command do I use to get a sparse matrix between points? So the exercise is related to getting help on Python objects or functions. So our options are, just like in the text box up here, help. Let's go with the initialize object KD, although I think they return the same doc string when you ask for help with each one. Okay, what's going on here? So it prints out information about the class, class being the template for the object that we're dealing with. The parameters that it takes in, so we'll remember that we put in the array coordinates. We left the leaf size, optional argument blank. And then below we have some information about the algorithm, and then some methods that the object can do. Methods being functions that belong to an object. Count neighbors, query, very nice. And we want sparse distance matrix. So the arguments to the sparse distance matrix, it says self, which I'll cover again in a tutorial when we talk more about objects, but that indicates that that's an argument that will be left blank. It automatically gets filled in by the parent object. Other. So the other will be another KD tree. And we need a maximum distance as well. And I have to admit, when using the other, I was a little thrown off with whether or not I was actually doing this right. So hopefully I can rectify it by next time and find out what's going on. But I'll show you what I mean. So to find the sparse distance matrix, we want to use KD dot sparse distance matrix function. And what does this come up with? So a question mark at the beginning or the end of a line of code will also bring up a help box, which in the case of this particular notebook brings up a nice little side panel. So the parameters are a KD tree and the maximum distance. So my confusion with this is because we already refer to the KD object by calling the function from it, and then we feed it again. So that's where I get confused, but I'm sure there's a sensible answer. And the other parameter we need is max distance, and for now I'm going to set it as 10. And I put a dot over the end of the 10 because max distance has to be a positive float. Okay, and then that returns ideally our sparse distance matrix. So what's happening here, and why is it taking a second to compute? Well, you might remember that when we initialized our KD tree, it happened more or less instantly. So at this point, now the distances between the points are actually being calculated. And even though the size of the job is far smaller than it would be if we were doing the distance between every single atom and every single other atom, it still does take some time, but it's quicker. So I suppose we can't complain too much. Okay, so that is the last exercise of the session. Alex Henderson's point in the chat For super users, there is a drop-in replacement for Conda called Mamba. Super user being the Mac and Linux equivalent of a Windows admin. Gives you special privileges, say, called Mamba. So that's something that if you are an admin or a super user on a Mac or Linux machine, then you can use Mamba. Presumably it's a package manager for a speed up. The second point, if you run pip on a Linux box, for example, what we're viewing at the moment, you will import packages onto the system Python. So many Linux computers come pre-packaged with Python as a built-in language. And Alex quite rightly points out that that's the version of Python to which modules will be installed if you use pip. However, if you have installed Python via Anaconda, then the default Python will be the Anaconda version of Python. So by using pip, if you've already installed Anaconda with your default Anaconda Python, then that's where the packages will go, which is handy. But yeah, Alex is right. If it's a built-in Python and if any external or third-party software is dependent on your built-in Python and you start sort of polluting it with modules here and there, then that could potentially lead to problems. Yeah, that's right. Okay. Well, it's just gone past 1 o'clock now. Thank you everybody for coming. Next week, we will continue with our distance calculations, and we will also look at the graph data structure, which is networks, pretty much. We'll treat our protein like a network of bonds and do some analysis based on that. Before we finish up, are there any last questions, comments, suggestions, notifications, anything at all? Okay, well, in that case, yeah, thank you everybody, and I'll see you again next Friday, where we will do more back to basics Python. All right.
Cheers, James.
Bye. Bye, everybody.
Bye. Thank you.
Bye bye.